Hey guys, today we're going to learn about inverses of functions. Now a couple things to remember and keep in mind as we work today. Recall that a relation is any pairing of the elements of one set, which are the domain, with elements of a second set, which is the range. So basically what this means is that a function is a relation where one x leads to exactly one y. The elements of the domain are your inputs, which are your x values, and the elements of the range are the outputs, which are the y values. In a one-to-one function, no output, meaning y, is used more than once. So that means that there is exactly one x for one y. Neither x nor y value repeats. In a many-to-one function, at least one output is used more than once. So that means that there are many x's for one y. So hence why it's called a many-to-one. Now specifically for inverses, inverses are when your x and your y's switch places. And that's because the function reverses the pairings of the relation. If a relation is expressed as an equation, its inverse can be found by interchanging the x and the y value. And the inverse of a function may or may not be another function, which is what we're going to investigate now. Now here we have a little graph, or rather a visual representation of a function. We have the domain, which is the -4, 0, 1, and 4, and then the range, which is -2, -3, 2, and 1. Remember, domain x's, range y's. So if this is a function, its inverse is when your x and your y values change places. So the -4, which was an x, is now the y, and the -2, which is a y, is now the x. So that means that for when x is -3, the y value would be 0, and when x is 2, the y value would be 1. So this would be considered the inverse of the function, and that's just taking the x's and the y's of the original function and switching places. Now the function, as you can see, 1x goes to exactly 1y. This makes it a one-to-one function. Now its inverse, when you have a one-to-one function, meaning only x's and y's, they both don't repeat, then the inverse is also a function. And that's because, as you can see from all of the x's, no x repeats. As a reminder, your one rule for functions is that the x values cannot repeat. Now over here, these are your same function values. So that means that for this x is -3, the y is still 0. And for this 2, the y is also 1. Now as you can see here, we have many x's that go to one y. So this function would be considered a many-to-one. Now when you have a many-to-one function, the inverse is not a function. And this is because your x values would repeat in terms of the inverse. See here, if we have x is equal to 2, when we replace the domain and the range and we switch them, the 2 has the y value of 1 and the y value of 4. That means if I write these coordinates of the inverse, I would have 2, 1 and 2, 4. You see how the x's repeat, making the inverse not a function. Now in this last question here, it says, what do you notice about the domain and range of functions and their inverses? Now because your x's and your y values switch place for your inverses, and the x's represents domain and the range represents your y's, that means that domain and range also switch places. So essentially, the domain of the function is the range of the inverse, and vice versa. So the range of the function is now the domain of the inverse. Now over here, I have given you function values, which are the same coordinates that we were dealing with earlier, -4, -2, 0, -3, 1, 2, and 4, 1. Now for the inverse function, that just means that the x and the y values switch places. So for the -4, -2, your new coordinate would be -2, -4, followed by -3, 0, 2, 1, and 1, 4. Now if I were to plot these points on this graph, now these points here in black are your function points. Now I'm going to plot my inverse function points. So I have -2, -4, -3, 0, 2, 1, and 1, 4. And if you can tell, here we have this line here, I'm just drawing over it. This is y is equal to x. When you plot your function and the inverse, they are a reflection along that line. As you can see, each point is on the opposite end, like each point of the function and the inverse, they're on opposite ends of that y is equal to x line. So when you graph the function and its inverse, the relationship is that they are reflected. And they are reflected along the line y is equal to x. So these are just a couple of things to keep in mind when we're working with inverses. Your x and y switch places, and graphically it would be a reflection along the line y is equal to x. Now, in order for us to verify if a set of functions are inverses, which we're going to be doing, we will need to be able to find the composition of functions. Now, a composition is simply another operation. An operation is anything like plus, minus. Those are all symbols of operations. It means to add or to subtract. Now, for a composition, the operation is this symbol right here. It looks like an open circle. And what that means is that your first letter, which is your first function, is the outer function. And then the second letter would be your inner function. That is the one that you put inside of your other function. So how do we do this? Here we have f of g of x. Now this is not related to inverses. This is just so you understand how to complete a composition, so that when we do this with inverses, you know what to do. So first we're going to take f of x. And what I'm going to do is I'm going to just copy it down exactly as I see it. But instead of writing x, I'm going to replace x with parentheses. So this is x plus 1. That is my f of x. Now you'll notice that inside of f, in that bracket here, will be g of x. So what that means is that inside of the parentheses, that's the inside, right? I am going to put g of x, which is 2x. This is my composition. So once you have this done, then you can simplify as much as you can. But here there's really nothing else for me to do, so it would just be 2x plus 1 as my answer. Now if I do g of f of x, now instead of, it's the other way around, so g is your main function. So this is the one that's going to be on the outside. So I'm going to copy it down, but instead of x, I'm going to open parentheses and leave it blank. And now for the inside is f of x. So I'm going to take f of x and put it inside of the parentheses. So I'm going to write x plus 1 in here. Now we would simplify. Now we can see this 2 needs to get distributed. So this would equal to 2x plus 2. So these are how you do compositions. So remember, the first letter, the one that is on the outside, that is your main function. It is going to be the one that you copy down first. And then where you put your parentheses to represent your x's, that's where you put the second function, the one that is on the inside. So let's practice this. So here, this first one is f of g of x. So I'm going to take f and I'm going to copy it down since that is my first function. So 2 parentheses for the x minus 3. And on the inside, I'm going to copy down g of x, which is x plus 5. And now I would distribute the 2. So 2x plus 10, and then this minus 3, which when we simplify is simply 2x plus 7. Now let's try this with g of f of x. Since g is on the outside and it's the first letter, that is my main function. So we're going to copy it down. Instead of x plus 5, I'm going to put parentheses for the x plus 5. And on the inside, I'm going to copy f. Since f is on the inside of that bracket, it is what gets plugged inside of g. F, which is 2x minus 3, would go in here. Now there's nothing to distribute, so all I'm going to do is combine like terms. So we have 2x minus 3 plus 5, which would equal to 2x plus 2. Let's try with another function. We have f of x is equal to 1 minus x, and g of x, which is equal to 3x plus 4. So for a, we have f, which comes first. So I'm going to copy down f exactly as I see it. So 1 minus parentheses for the x. And on the inside, I am going to put g of x, which is 3x plus 4. Now here, even though you don't see it, it's minus this, so that means we're going to have to distribute a negative into the parentheses. So this will give me 1 minus 3x minus 4, which would equal to negative 3x minus 3. And now lastly, we have g of f of x. So I'm going to copy down g, so 3 parentheses for the x plus 4. And inside of the parentheses, I'm going to put f, which is 1 minus x. I'll distribute 3, which would be 3 minus 3x, and then this plus 4, which when you combine like terms would give me negative 3x plus 7. All right, so now why do we learn how to do this? When we are verifying two functions, if they are inverses, what you're going to have to do is find f of g and g of f. And if they are inverses, both of these compositions would equal to x as your final answer. So let's try this out. So I have functions f of x is equal to 4x plus 1 and g of x, which is equal to x minus 1 all over 4. I want to check, are these inverses? So I'm going to go ahead and first find f of g of x. So f is the one on the outside, so I'm going to copy down f exactly as I see it. So 4 and then parentheses for the x plus 1. And then inside is g of x, so I'm going to copy down g of x in my parentheses, which is the x minus 1 all over 4. Now remember, although this is a fraction, please keep in mind that fractions are just division. So if I'm multiplying 4 on the outside and I'm dividing 4 on the inside, they cancel. And so all that's left now is x minus 1 and finally plus 1. The 1's cancel and our final answer would be x. So far everything's looking good. But now you also have to do g of f of x. So now I'm going to copy down g as I see it. So parentheses for the x minus 1 all over 4. And inside the parentheses, I'm going to copy f, which is that 4x plus 1. The first thing that I can cancel would be these 1's. I have a plus 1, I have a minus 1, so bye. So now all you have left is the 4x over 4, And now these 4's would cancel because it's like basically 4 divided by 4. And you see we end up with x again. So this verifies that f of x and g of x are inverses. And that's because both f of g of x and g of f of x are both equal to x. Alright, so now the last thing, well, sort of the last thing that we kind of need to do with inverses is how to actually find that inverse equation. Okay, so we have f of x is equal to 3x plus 4, and I want to know what is the inverse for f of x. And I put some steps here for you to follow so that we can go ahead and find that inverse. First, we're going to substitute y for f of x. Remember that f of x is just function notation, but it represents y. So y is equal to 3x plus 4. So that's step 1. Your second step is to switch the x and the y. And we do this because that's the definition of an inverse, when your x and your y values switch places. So instead of y, I'm going to write x is equal to 3y plus 4. So I just switch the location of x and y. That's step 2. Step 3 is now to solve for y, meaning I'm going to move everything over to the other side with the x. So first we would subtract this 4. So x minus 4 is equal to 3y, and then divide the 3. So everything gets divided by 3. So this is my inverse here. So that's step 3. But remember, in upper level mathematics, notation is really important. This is not just another function. This is to signify that this is the inverse of f of x. So I'm going to use the notation f, and it looks like a little exponent of -1 of x. What this means is f inverse of x. So that little -1 signifies that this is the inverse of our function. So f inverse of x is equal to x minus 4 all over 3. Now, once we have found our inverse, we are going to verify that our answer is correct by finding their compositions. If you do not get that the composition is equal to x, then that means something went wrong, and try again. Go back and check your work where you found your inverse. So here we go. So as you can see from this notation, f is on the outside. This is f. So I'm going to copy down f as I see it. 3 parentheses x plus 4. And inside the parentheses is f inverse. So that's what I'm going to write inside. The x minus 4 all over 3. This 3 is being multiplied. This 3 is being divided. We can cancel it. So now we just have x minus 4 plus 4. And those 4's can cancel. So we get our final answer here of x. So far, everything looks good. Now we got to do it the other way around. See, on the outside is f inverse. So I'm going to copy down my inverse equation as I see it, except where I have the x, I put parentheses. So x minus 4 all over 3. And on the inside of the bracket is my f of x. So I'm going to copy down f of x in there. So 3x plus 4. First in the numerator, the 4's can cancel. So this leaves me with 3x over 3. And now these 3's can cancel, and I'm left with x. And since both of my compositions are equal to x, this means that my answer was correct, and I did indeed find the correct inverse. Okay, so now we're going to put everything together. We're going to find the inverse of the function below, use compositions to verify that the functions are inverses. Then we're going to graph the function and its inverse. So here we go. We have f of x is equal to -2x plus 3. So in order to find the inverse, I'm first going to replace f of x with y. Now I'm going to replace y with x and x with y, so switch places. So x is equal to negative 2y plus 3. Now we solve for y. So I'm going to subtract the 3 first, and we get x minus 3 is equal to negative 2y, and then we would divide everything by negative 2. This would be my inverse, so remember the proper notation. F inverse of x is equal to x minus 3 all over negative 2. This is my inverse. Okay, now that we found the inverse, we need to verify by compositions. So first, I'm going to find f of f inverse of x. So meaning my function is going to go on the outside first. So negative 2x plus 3. Inside would be my inverse, which I just found, so that x minus 3 all over negative 2. These negative 2's would cancel since one is multiplied and the other is divided. And so now all I have is x minus 3 plus 3. These 3's would cancel, which leaves me with x. So far, so good. Now we got to find the other composition. So we're going to do the inverse on the outside. So f inverse of f of x. So I'm going to copy my inverse now. So x minus 3 all over negative 2. And inside the parentheses, I'm going to write down my f of x. So negative 2x plus 3. Since I can't do anything else in my parentheses, I notice that I have this plus 3 and minus 3 in the numerator. So those 3's will cancel. And then I have negative 2x all over negative 2. So I can cancel out those negative 2's. And I'm left with my final answer of x, which is verification that these are indeed inverses. Now we're ready to graph. So first I'm going to graph f of x, which is negative 2x plus 3. Please remember that the equation of a line is y equals mx plus b. All of our functions and inverses are just going to be lines. So in order to graph a line, remember that we need the y-intercept first. In this particular equation, my y-intercept is 3. So I put my first point on the y-axis when y is equal to 3. And then I use the slope to figure out my very next point. For this, my slope is equal to negative 2. Now with slope, it's easiest if you have it as a fraction. Any whole number is always over 1. So this means that my slope, as a reminder, which is rise over run, the numerator tells you whether to go up or down. The denominator tells you to go left or right. So since the numerator is negative 2, that means I'm going to go down 2. And because the denominator is 1, I'm going to go to the right 1. So that's my second point. And what I like to do, just because I can't really draw straight lines, I'm really bad at it, I just kind of follow that same pattern until I get to the edge of my graph. So that way I can have a really nice line. This is my function. Now we're going to go ahead and graph the inverse. Now the inverse does not necessarily look like y equals mx plus b, because what we have for the inverse, as you can see, is this x minus 3 all over negative 2. But what we can do is split up that fraction. And what I mean by that is everything here, this x is divided by negative 2, and that negative 3 is also divided by negative 2. So I'm going to split this up. So this is x over negative 2 minus 3 over negative 2. Now again, I want to write this in a way that I can kind of like really see what that slope is and just simplify this a little bit. When there's nothing in front of the x, that's the same as a 1. And when you have a negative in any kind of your fraction, you can either put it in the numerator or put it in the denominator. It does not matter. It means the exact same thing. Because remember, since fractions are division, if you divide a negative number by a positive, or if you divide a positive number by a negative, it doesn't matter. Your whole thing will end up being negative anyway. So I always just put my negative in the numerator. So this would be negative 1 over 2, because of this, 1 over negative 2, x on the outside. And then a negative 3 divided by negative 2 would give us a positive number. So plus 3 over 2. This is better now, right? We have our slope, which is negative 1 over 2, and our y-intercept, which is 3 over 2, which is the equivalent to 1.5 if you divide 3 by 2. So that means my y-intercept, I'm going to go to 1.5, which is right here in between 1 and 2. And then my slope is negative 1 over 2. So I'm going to go down 1, right 2. Down 1, right 2. Or if you left the negative in the denominator, then it would be up 1, left 2. Up 1, left 2. And again, we would connect the dots. And this would be my inverse. So that's how you graph. And when you graph, you'll notice that it's a reflection on y is equal to x. Your two lines should intersect somewhere on that line y is equal to x. Let's try this all over again just to make sure we got it. So our final example. We have f of x is equal to 2x minus 2. So remember to find the inverse, replace f of x with y. Now we switch places with x and y. And now we're going to solve for y. So I'm adding 2 to both sides. X plus 2 is equal to 2y. And then we're dividing by 2. So my inverse is equal to x plus 2 all over 2. Now I'm ready to start finding those compositions. So let's start with f of f inverse. So remember, this means that my function is the one that is on the outside. So I'm going to copy that down. 2 parentheses for the x minus 2. And on the inside, I'm going to write my inverse, which is x plus 2 over 2. Now here, I can cancel out these 2's because they're being multiplied and divided. And so I'm left with x plus 2 minus 2. And those 2's can cancel, which equals to x. Now I can go ahead and find the inverse. The composition of the function on the outside. Your inverse on the outside, function on the inside. Now it doesn't matter which order you choose to do first. Like I always do the function and then the inverse on the inside first. You can do whichever one because either way you have to do both. So we're going to do the inverse. So I'm going to copy down the inverse, which is the x plus 2 over 2. And inside the parentheses, I'm going to write my function, which is the 2x minus 2. Now, these 2's would cancel out first. You always want to simplify your numerator as much as possible before you move on. And this equals to 2x over 2, which those 2's cancel. So I'm left with x. So my compositions check out. They both equal to x, meaning that my inverse is correct. Okay, so now let's go ahead and graph the function. So my function is 2x minus 2. Again, mx plus b. My y-intercept is negative 2. And my slope for this is 2 over 1. Meaning I'm going to go up 2, right 1. Up 2, right 1. And I just kind of follow that pattern until I reach the ends of both graphs. So that way I get a nice straight line. As much as possible, right? Okay, and now we're going to go ahead and graph the inverse. My inverse, I need to rewrite this so that it is in y equals mx plus b form. Remember, if everything is over the same number, you can split this up. This is the same thing as x divided by 2 plus 2 divided by 2. Now, if there's nothing in front of the x, remember that's a 1. So this is 1/2 x plus, and now 2 divided by 2 is 1. So that means that my y-intercept is 1. And I'm going to go from here, up 1, right 2. Up 1, right 2. And the same in the other direction. And then these will be your inverse. And that's finding inverse functions and graphing and verifying.